Imagine a fault line stretching over 1,000 kilometers along Canada's west coast, a seismic threat capable of unleashing a magnitude 9 earthquake at any moment. Such a quake would send a 10-story high tsunami crashing onto shores from Alaska to California within minutes, threatening over 1 million lives directly in its path. What makes this danger even more alarming is that scientists have largely ignored this fault for decades. This is the Queen Charlotte Fault, one of the fastest moving and most tectonically active faults on Earth. It marks the boundary between the Pacific and North American plates, situated just off the coast of British Columbia. These colossal plates are grinding past each other at a pace comparable to the San Andreas Fault in California. Unlike the San Andreas, which has been extensively depicted in disaster films and studied in countless scientific papers, the Queen Charlotte Fault remained in the shadows until recent years. That changed when, several years ago, an earthquake with a magnitude of 7.80 struck the Haida Gwaii Islands. The tremors were felt hundreds of kilometers away, and a small local tsunami was triggered. Fortunately, casualties were avoided due to the sparsely populated islands, but the event sounded an alarm to the scientific community. The earthquake's unusual nature was particularly concerning. Instead of the typical horizontal slip seen in transform faults, it involved vertical movement, with one plate subducting beneath the other. This indicated that the Pacific plate was beginning to dive beneath the North American plate, a process known as subduction. Subduction zones are notorious for generating some of the planet's most powerful earthquakes. Think of Japan in Dvei Tisuchi Odinitsit when a magnitude 9 quake caused the Fukushima nuclear disaster, or the Dvei Tisuchi Chitture Indian Ocean tsunami, which affected 14 countries after a magnitude exceeding 9 struck in a subduction zone. Now, it turns out that the Queen Charlotte Fault in Canada is also part of this dangerous subduction system. The story, however, is only just unfolding. Just 4 months after the Haida Gwaii quake, the fault reawakened near the town of Quake in Alaska, producing a magnitude of 7.5. This time, the mechanism was different. A straightforward right lateral strike slip, with the plates sliding horizontally past each other. The fault demonstrated its unpredictable nature once again. In response, international research teams swiftly organized an expedition that yielded unprecedented, high-resolution images of the fault structure. These findings forced scientists to reconsider previous models. They discovered that the Queen Charlotte Fault is not a single continuous segment, but comprises 4 distinct sections, each with unique characteristics, movement patterns, and associated risks. This revelation underscores the complexity and potential danger lurking beneath the Pacific Northwest surface, highlighting the urgent need for ongoing study and preparedness. The most perilous segment stretches from the northern reconnection zone across Washington to the southern part of British Columbia. Here, the Earth's crust appears flatter and smoother, indicating that tectonic plates are firmly locked together. Instead of slipping gradually, stress accumulates over time until it reaches a breaking point, resulting in a catastrophic rupture. Professor Kenneth MacDonald of the University of California has issued a groundbreaking statement that challenges previous predictions. It was once believed that such a massive earthquake might occur in tens of millions of years. Now, scientists realize the process is progressing much faster than anticipated. Alarmingly, the last significant quake in this region happened in the year 1700, over 3 centuries ago. meaning enormous energy has been building up all this time. The anticipated magnitude of the next major earthquake could reach 9 or even higher. To put this in perspective, in California's San Andreas Fault, the maximum expected magnitude is around 8.3. Although the difference seems slight, the magnitude scale is logarithmic. Each whole number increase roughly multiplies the energy released by about 30 times. Consequently, a 9-point earthquake would unleash nearly 1,000 times more energy than an 8-point quake. The impact zone would include Canadian cities such as Vancouver, Victoria, and Whistler, as well as American urban centers like Bellingham, Seattle, Tacoma, and Olympia. The total population at risk exceeds 4 million people, considering only the direct effects of the tremors. A tsunami generated by such an event could reach 30 meters in height, sweeping inland for hundreds of kilometers and destroying everything in its path. For those interested in these topics, there is a Telegram channel where additional content is shared, material that, for various reasons, doesn't make it onto YouTube. There you can find exclusive satellite images, insider insights from analysts, strange and dangerous events, all designed to provoke reflection on what is happening on our planet. The link is available in the description below this video and in the pinned comment. Moving on to YouTube, the picture becomes even more ominous. The Queen Charlotte Fault connects with the Cascadia Subduction Zone, a 600-kilometer-long fault line stretching from southern Canada to northern California. What makes Cascadia particularly terrifying is its unusual silence. Most active faults regularly release energy through small and medium earthquakes, but Cascadia remains eerily quiet, quietly accumulating stress for decades without any signs of activity. When it finally releases, the quake will be so powerful that seismic waves will travel from Vancouver to another continent. This last major event occurred on the 26th of January, in the year 1700. Remarkably, scientists know the exact date, despite the region lacking seismographs or European settlers with written records at that time. How is this possible? The answer lies in Japanese historical chronicles. On that day, a massive tsunami struck Japan's eastern coast without any preceding earthquake recorded locally. The waves seemed to come from afar, and researchers have correlated these accounts with geological data from the American coast, confirming the event's timing with astonishing precision. A powerful earthquake, registering nearly 9 on the Richter scale, tore across Cascadia from edge to edge, unleashing devastation. Within 48 hours, a tsunami swept through the Tikokian region, inundating Japan and causing widespread destruction. Though 325 years have passed since then, Cascadia remains silent. Yet beneath this calm lies immense tension. Emergency experts in Varagon and Vishington have conducted complex modeling, revealing results so startling that they hesitated to publish them for a long time. Now, the most intriguing part emerges. Recent studies indicate that Cascadia and the Queen Charlotte Fault are not merely neighboring structures, but are interconnected far more deeply than previously believed. When scientists obtained detailed images of the ocean floor, they uncovered an unexpected yet significant phenomenon. Seismic signals are transmitted between these systems through an intricate network of fractures and deformations within Earth's crust. This suggests that a powerful quake in one area could trigger a chain reaction elsewhere. Adding to the concern, researchers identified a critical zone where the Queen Charlotte Fault intersects with the Cascadia region, known as a triple junction. This is a point where 3 tectonic plates converge: the Tikokian plate to the north, the North American plate, and a small microplate called Explora. A series of expeditions led by scientists from the University of British Columbia utilized underwater robots equipped with high-resolution cameras and seismic sensors to investigate this area. Their findings on the seafloor were alarming. Recent underwater landslides, cracks in the oceanic crust, and signs of active volcanism all point to a region under extreme stress. The Earth's crust here is on the verge of rupture, and a major seismic event could occur at any moment. Meanwhile, beneath the continent, something equally unsettling was uncovered. Ancient faults, long considered dormant for millions of years, are far from dead. In 2024, researchers from the University of Victoria published a groundbreaking study revealing that the Tentina Fault, located in northwestern Canada, which had shown no activity for over 40 million years, is now accumulating strain. This fault stretches over 1,000 kilometers across Yukon and Northern Territories, having shifted approximately 450 kilometers over its history. The scientists concluded that the Tentina Fault is nearing the end of its seismic cycle, with accumulated deformation potentially unleashing an earthquake exceeding magnitude 7.5. This area, previously deemed safe, hosts major cities, mines, and critical pipelines, making the threat even more alarming. To understand the full picture, it's essential to grasp how these faults are interconnected. The Earth is composed of separate, seemingly independent pieces, yet it functions as a dynamic, unified system. A disturbance in one part can send vibrations rippling across the entire planet. The Tentina Fault is directly linked to the Denali Fault in Alaska, forming part of a vast network of transform faults that transmit deformations from the Pacific coast deep into the continent. This interconnected system means that seismic activity in one region can influence distant areas, amplifying the potential for widespread upheaval. In essence, the Earth's crust is a fragile, interconnected web of faults and fractures, where stress accumulates silently until it suddenly releases, often with catastrophic consequences. The recent discoveries underscore the urgency of understanding these hidden links, as the planet's seismic activity remains unpredictable and potentially devastating. On the 3rd of May, 2002, a major fault line suddenly ruptured due to a powerful earthquake measuring Sem Tochka Vosum on the Richter scale. The fracture stretched over 34 kilometers, roughly the distance from Parija to Burvseli, forming a continuous crack across the landscape. Fortunately, the region's sparse population meant there were no casualties, but the event revealed something crucial about Earth's seismic behavior. Prior to this quake, the Denali Fault had remained relatively stable, experiencing only about 4 minor tremors annually. However, in the 8 months leading up to the disaster, microseismic activity intensified dramatically, with 80 small quakes recorded, far above the usual 3 or 4. It was as if the Earth was giving an early warning of the impending rupture. After the Dve Tisici Dva earthquake, seismic activity gradually shifted eastward, moving toward the Tenti Fault. This migration resembled a slow wave traveling across the fault system, with small earthquake epicenters drifting along the line at a rate of several kilometers per year. The connection runs even deeper beneath the surface. In the upper mantle, streams of fractured material, known as mantle plumes, rise from the Earth's depths. These hot, molten flows ascend through the crust, causing it to swell and crack. One such plume is located beneath Yellowstone, the famous supervolcano in the United States. Few realize that this plume influences more than just Yellowstone. It affects the entire northern American crust. Over the past 17 million years, this mantle upwelling has interacted with ancient calderas and volcanic remnants, tracing a chain from the Yellowstone region southward to Wyoming. The deformation caused by this plume propagates across the northern United States and southern Canada, creating zones of tension and fracture. The stresses induced by these mantle flows generate a vast interconnected network of weak points in the Earth's crust. These zones are not isolated but form a complex web of vulnerabilities. Consequently, scientists now study these faults collectively, viewing the entire system holistically rather than in isolated segments. The overall picture is rather ominous. On May 1st in 2017, a series of earthquakes struck along the border between Alaska and British Columbia. In just 24 hours, 62 tremors were recorded, two of which exceeded magnitude 6. Such intense activity alarmed seismologists, prompting increased concern. Then, in March of 2024, nearly 2,000 earthquakes occurred in a single day beneath Vancouver Island. This equates to roughly 200 tremors per hour, or more than 3 every minute, an almost continuous rumble beneath the Earth's surface. What caused this surge? Researchers believe that magma intruded into the oceanic crust beneath the region, forcing its way upward through fractures. This molten rock, rising from deep within the Earth, fractured the surrounding layers and created microcracks. The Juan de Fuca Ridge, where these earthquakes were concentrated, is an active spreading zone where tectonic plates diverge, allowing magma to ascend. Interestingly, this heightened activity coincides with a period when the entire fault system in the area is under increased tension. The timing suggests a possible link. The current stress buildup may be facilitating magma movement, or perhaps the magma ascent is a response to the regional tectonic stresses. Whether this is mere coincidence or a sign of an impending larger event remains uncertain, but the pattern underscores the interconnectedness of Earth's dynamic processes. Scientists have increasingly uncovered strange connections between various geological processes, such as the melting of glaciers in Alaska and Canada. As climate change accelerates, glaciers retreat, seemingly influenced by seismic activity. The immense weight of glaciers, sometimes several kilometers thick, presses down on the Earth's crust, causing it to bend under the load. When the ice begins to melt and the glacier thins, the crust gradually rebounds, leading to complex stress redistributions. This rebound often generates additional tension, especially in regions already fractured by faults. Research conducted near Hudson Bay has revealed a rise in small earthquakes, with magnitudes ranging from 3 to 5. While these tremors are not catastrophic, their increasing frequency signals a concerning trend. Human activities further complicate the picture. Extraction of oil and gas, water injection into deep wells, and the creation of reservoirs all alter subsurface pressures. These anthropogenic influences can trigger earthquakes, known as induced or technogenic events, which are becoming more common. For instance, in the Canadian province of Alberta, known for its oil sands, seismic activity has surged markedly. Before the advent of extensive shale oil extraction, the region experienced roughly 10 earthquakes annually. Since hydraulic fracturing began, that number has soared to over 100, an increase of tenfold, despite being located relatively close to fault systems like the Denali and Tinta faults. Some experts warn that these induced tremors could act as a spark, igniting larger seismic events. The year 2017 marked a turning point in understanding Canada's fault systems. A team of researchers embarked on an expedition aboard the research vessel Ocean Star, uncovering startling findings. High-resolution seismic imaging revealed previously undetected faults beneath the seabed, hidden fractures not visible on the ocean floor but clearly identifiable on seismic profiles. These concealed faults, dubbed Sitka Sound Fault, lie beneath the continental shelf west of the town of Sitka, Alaska. The images showed deformed and displaced sediment layers indicating recent activity. Even more intriguing was the discovery of deformation along the Queen Charlotte Fault on the Pacific Plate. Sedimentary layers on the oceanic crust appeared twisted and torn, signs of active folding and compression. This suggests that the oceanic crust is under immense pressure, which is steadily increasing. To better understand these processes, scientists developed computer models simulating conditions deep beneath the surface. The models revealed that the Queen Charlotte Fault does not merely slide past the North American plate. In its southern section, it begins to subduct the continent itself. The angle of subduction is relatively gentle, around 5 to 8 degrees. But even this modest inclination generates significant stress accumulation. Seismic sensors placed near the Haida Gwaii Islands recorded reflections of seismic waves from the descending slab at depths between 12 and 36 kilometers. These findings underscore that the Earth's crust in this region is under intense, ongoing deformation, with potential for sudden release of energy in the form of earthquakes. In summary, ongoing research highlights a complex interplay of natural and human-induced factors shaping seismic activity. Melting glaciers, tectonic plate interactions, and industrial activities all contribute to the evolving seismic landscape, often in ways that remain hidden beneath the surface, but carry profound implications for the stability of the region. Beneath the archipelago lies a fragment of oceanic crust that has gradually descended into the mantle, a process responsible for uplifting the islands above. This dynamic explains why Haida Gwaii features towering mountains, where active erosion exposes increasingly ancient rocks. The land responds to pressure from below, causing the islands to grow and the terrain to rise. Eventually, this tectonic stress culminates in catastrophic events, releasing built-up energy suddenly and violently. Imagine a major earthquake triggering multiple landslides simultaneously along the coast. The resulting tsunamis from these landslides would arrive faster than seismic-induced waves. In such moments, there will be hardly any warning time for those living nearby, leaving communities vulnerable to rapid, destructive surges. In July of 2025, a groundbreaking scientific paper challenged previous notions about Canada's seismic hazards. Researchers from the University of British Columbia, Canada's Geological Survey, and American experts introduced a comprehensive model that integrates all regional faults into a unified system. This model revealed that faults are interconnected not only through mechanical stress transfer, but also via deep mantle processes. Beneath British Columbia, scientists identified a zone where seismic wave speeds decrease, indicating hotter, partially molten rocks, an area akin to a mantle plume rising from deep within the Earth. This hot flow feeds the Cascade volcanoes but also exerts additional pressure on the base of the lithosphere. The most alarming discovery was that geochemical analyses of geothermal gases from Ken and other distant sites contained elements that could only originate from the Earth's deepest layers, possibly near the boundary between the mantle and the core. Similar anomalies found near Cascade volcanoes suggest that processes occurring over 2,000 kilometers beneath the surface influence seismic activity at the surface. Furthermore, researchers observed a peculiar periodicity and regional seismicity. Major earthquakes in the Queen Charlotte Fault Zone, along the Alaska-Aleutian Subduction Zone, and within the Cascadia region often occur in correlated patterns. Significant tremors in one area tend to be followed or preceded by large quakes in another, with intervals spanning several years or decades. For example, the Cascadia earthquake of 1700 occurred a few years after intense seismic activity in Alaska, while the 1949 quake on the Queen Charlotte Fault was linked to earlier events on the Alaska-Aleutian segment. Vancouver, home to over 2.5 million residents, Canada's third largest city, stands perilously close to these fault zones. Situated less than 200 kilometers from the Queen Charlotte Fault and directly above the Cascadia subduction zone, the city faces immense seismic risks. Modern Vancouver, a bustling metropolis with skyscrapers, a busy port, bridges, tunnels, and an international airport, is built under some of the world's strictest seismic building codes. These regulations ensure that structures are designed to withstand powerful earthquakes, reflecting an awareness of the region's geological hazards and the need for resilient infrastructure. The core issue lies in the fact that much of the existing infrastructure was built long before scientists fully understood the scale of the threat. In British Columbia, authorities have already launched a comprehensive modernization program, focusing on strengthening power grids, reinforcing bridges, stabilizing foundations in hospitals and schools, and establishing backup water and energy systems. These efforts will require billions of dollars and decades of work. However, there is concern whether they will be completed before a major seismic event strikes. Particularly vulnerable is port infrastructure. Vancouver, Canada's largest Pacific port, handles the majority of Asian cargo imports. If an earthquake or tsunami were to disable this port, the entire country's economy could suffer a severe blow. Additionally, thousands of people living in the area could be directly affected. The city itself is partly built on loose sediments that, during an earthquake, could liquefy and cause widespread destruction. The Dve-Tisichi-Odinitsit Christchurch earthquake in New Zealand demonstrated this risk vividly, forcing entire neighborhoods to be demolished and rebuilt. Small coastal towns face even greater peril. Many lack the resources to retrofit their infrastructure and are often situated at river estuaries or low-lying shores. These communities are the first to be hit by a tsunami. After the Dve-Tisichi-Chatirai Indian Ocean earthquake and tsunami, some coastal villages were completely wiped out, leaving only barren land and debris behind. Some optimists argue that increased seismic activity is a sign that the Earth is releasing pressure gradually, reducing the likelihood of a major catastrophe. Yet, geological history suggests otherwise, as periods of heightened activity often precede large-scale events, similar to a cough warning of a more serious illness. In summer of 2025, Canada's Geological Service released an updated seismic risk map. The high-risk zone has expanded, now encompassing not only coastal regions but also inland areas reaching Yukon and the northern parts of the Western Territories. Certain faults, such as the tectonic fault, are officially recognized as potential sources of powerful earthquakes. Japan's residents are well aware of their dangerous location, conducting regular drills, adhering to strict building codes, and cultivating a culture of disaster preparedness. Despite this, thousands perished in the Dve-Tisichi-Odinitsit earthquake because it is impossible to be fully prepared for every scenario. Now, this threat looms over Canada and the northern United States west coast. Faults that had remained silent for centuries have been dormant, lulling populations into false security. The geological history warns that periods of increased seismic activity often precede major quakes. If such an event occurs, the consequences could be devastating, impacting millions and causing widespread destruction.